Hi students, in this video lesson I am going to discuss about compilers. So, compiler is a system software which converts a program written in high level language, that is the source language, to low level language, that is the machine language. So this diagram shows how the compiler basic operation performed by the compiler. So the input is the high level language program and output is the low level language program, that is the machine language program. So the compiler validates the input program as per the language grammar and produces error messages. That is, while conversion, if there is any error, that is the syntax errors are given by the compiler. So normally for every high level language has a grammar. The grammar specifies the syntax of the legal statements in the language. So the source program statement is a sequence of each statement in a program is a sequence of tokens. So for example, if A equal to B, where if is a keyword and A is a variable and equal to is an operator, that is W equal to symbol equality checking, and B is an operand. Right? So every one will be treated as a token. So the tokens are the fundamental building blocks of the language. A token may be a keyword, a variable name, an integer, or an arithmetic operator, etc. The compilation is done in 3 steps, that is the lexical analysis, syntax analysis, code generation. So if for the compiler, the steps are represented here as a diagram. The source program is the input for the compiler. In the compiler, the lexical analyzer will tokenize the given source program. So the output of the input of the lexical analyzer is the source program and the output is the tokens. Those tokens are the input for the next step, that is the syntax analyzer. The syntax analyzer will check the grammatical validation of the given statements and construct the parse tree. And the next step is code generation. The code generation step will generate the target program, that is the machine language code. So these are the 3 steps that are involved in constructing a compiler. So compiler, it is a system software. It is a program. It is used to convert source language program into the target language program. Normally the source language is the high level language like C, C++, Java, and target program, that is the machine language program. Normally it is a object file. Here the first step of the compilation process is lexical analysis. So during the lexical analysis phase, the lexical analyzer scans the source statement and recognizes the various tokens in the source statement. It is performed by the scanner. The output of the lexical analyzer is a list of tokens. The syntax analyzer, the next step is the syntax analyzer. It analyzes the syntactical structure of the given input. That is, whether the statements in the source language program are in as per the grammatical rules. So here the grammar plays a major role. So the output of the syntax analyzer is a parse tree or a syntax tree. The next step in the compilation process is the code generator. The code generator generates the target code, that is the machine language code for the instructions in the source program. So the next topic here, these are the basic concept in compiler. So the compiler is a system software. It is used to translate high level language program into the low level language. So hence it is a translator. So the translation is done in 3 steps. that is lexical analysis, syntax analysis, and code generation. The lexical analyzer is also called as a scanner. The syntax analyzer is also called as a parser. The code generation process is done by the code generator. So the three steps. The input for the lexical analyzer is the source program. The output of the lexical analyzer is the list of tokens. Those tokens are given as input to the syntax analyzer. The syntax analyzer will construct the parse tree. That parse tree is the input for the code generation. The code generation will finally produce the executable file. Right. The next topic is grammar. A grammar for a programming language. So for every programming language like C, C++, Pascal, Java, whatever it may be the programming language, a grammar is available. A grammar is a formal description of syntax of programs and individual statements. So a grammar can be written in different ways. It may be a context-free grammar or it may be a package-nor form. In our textbook, they have discussed with the package-nor form. The package-nor form grammar consists of set of rules where each rule defines the syntax of the language structures. Here let us consider a simple program, that is, it is a simple Pascal program. Actually, in Pascal program, the first line, the program, then the name of the program. Then in every program, we need to declare the variables. For declaring the variables, the var keyword is used. And then the list of variables. Here sum, sq, I, value, mean, variance are the variables. The data types of those variables is given as integer. Then the blocking is done with the begin and end. Here it is in sum is initialized to 0 and sum of square sum sq is equal to 0. Here use the for loop. It is for I equal to 1 to 100. So begin within the for loop, read the value and sum equal to sum plus value, and one more thing, sum square equal to sum square plus value into value, that is sum of numbers and sum of squares of numbers. And next, after the for loop, mean value is calculated, that is sum divided by 100, and variance is calculated with the sum square divided by 100 minus mean into mean. Then finally write the mean and variance, that it will show the output. So this is a simple Pascal program. So this program is grammatically represented using the Backer-Snarr form is, that is here the first column, that is the sequence number. Then the second column is the list of non-terminals in the given program. So the non-terminals are represented within angle brackets, and the colon equal to this non-terminal is equivalent to. Here, for example, program, this is a non-term prog. Within angle bracket, it is a non-terminal. Then it is a program, that is the keyword. Then the name of the program, that is within angle bracket, it is a non-terminal. Then where, that is the keyword. Then the declaration list, begin, then the statement list, end. So this is the way, that is the structure of a program in Pascal. Starts with a program and program name and the variable declarations and the body of the program within begin and end. So in variable declaration we have the list of variables, and within begin and end we have the list of executable statements. The program name, it is once again, it is a non-terminal, and ID, it is a identifier, that is the user defined name. Then declaration list. So the user has to declare all the variables before they are used in the program. So that declaration list is once again a non-terminal, that can be a declaration dict or declaration list followed by semicolon. Right? Then declaration. Right? We can have any number of declaration within the program. Right? So the declaration list is consists of a list of identifiers, colon, type. In the previous example, the declaration is given by where, then the list of variables, and finally colon, the data type. So that is the grammar given here. right? So the declaration is ID list colon type. Here once again type, in this above example we have only used integer. So that is the data type. So this is the sample Backus-Naur form grammar, right? Likewise all the things. Suppose identifiers list. So the identifiers list means either it can be a single identifier or it can be a list of identifiers. So the list of identifiers are separated with comma. Right? Similarly, statement list. A statement or statement list semicolon followed by statement. So statement list is once again here the vertical bar symbol represents either a single statement or a list of statements. So it is a or option. Then similarly a statement. The statement can be a assignment statement or read statement or write statement or for statement. In the above example, these are the statements that we have used: assignment statement, read statement, write statement, for statement. For assignment, the syntax is ID is equivalent to. In Pascal, colon equal to is the assignment operator. Right? So the ID is the variable name is equal to the expression. Here once again the expression. The expression may be a single term or expression plus a term or expression minus a term. So these are the different options. The expression can be a single term or an expression with plus symbol or minus symbol. And the next non-terminal is term. It can be a factor or term into factor or term div factor. So into, that is the multiplication, this div is for division. The factor, once again the factor, it can be a identifier, that is the name of the variable, or int, it is a keyword, right? Or it can be an expression within parenthesis. Expression within parenthesis, because expression within parenthesis will be executed first, so to assign the priority. Then once again the read, it is used to get input from the user. So the read is the keyword and the ID list, what are the identifiers that we want to read from the user. Then once again for write, so it is used to display the result in the output. Then the for is a looping statement. Its syntax is for keyword and the index expression, that is for I equal to 1 to 100. So that is the index expression. That is one in the expanded in the next line. ID equal to expression to expression. That is I equal to 1 to 100. In the above example, you can know that. Then the body part is the list of statements. The statement that are with the statement within begin and end. Right? So this is a grammar for the above program. The above program is, it has the program name, variable declaration, and the body of the program within begin and end. This is the list of variable declarations. This is the assignment statement. This is also an assignment statement. This is a for statement. Begin. This is a read statement. Once again, it is an assignment statement. End statement. Assignment, write statement. So the grammar for each of these statements is represented in Backus-Naur form. So it can be is defined to be the symbol is equal to. The grammar can have both terminals and non-terminals. In the above grammar, all the symbols in the second columns within angle bracket are called as non-terminals. In the right side, the terms without angle bracket are called as the terminals. For example, ID, end, read, write. These are the non-terminals. So these are the terminals. So in a grammar, we can have both terminals and non-terminals. Terminals are enclosed within angle brackets. Non-terminals are not enclosed in angle brackets. Non-terminals are not enclosed in angle brackets. Right. So let us move on to the first step of the compiler, that is the lexical analysis. The lexical analysis is the process of converting a sequence of characters from the source program into a sequence of tokens. A program which performs lexical analysis is called as a lexical analyzer or scanner. Lexical analyzer or scanner. A token is a valid sequence of characters. In the above program, sum is a token, for is a token, right? Then to, begin, end, right? Even comma, semicolon, everything will be treated as a token. So the tokens may be a keyword, it can be a keyword, or it can be a constant, or it can be an identifier, or any numbers, operators, or punctuation symbols. Everything will be treated as a tokens. So the above program tokens, we have assigned the code. Actually these tokens are stored in the symbol table. Then the next, the lexical analyzer, for identifying the tokens, it can be implemented with the finite automata. The finite automata is often represented as a graphical format. So in this graphical representation, the first state, state 1 with the arrow, empty arrow, this is a start state. This double round circle, it is a acceptance state or the end state. Then the remaining are the states, and the arrows between the states are transitions, right? So these are the state transitions. In this example, suppose the input is ABC. So the first ABC, A actually valid input, it goes to the next state. Suppose the next input is B, it will goes to 3. And if it is the next input is C, then it will go to 4. That is, it reaches the final state or else the acceptance state. So when it reaches the acceptance state, the grammar accepts the input. Next, consider the second example, A, B, C, 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 A. The first A, it goes to the next state. From the start symbol, it's A, it goes to the next state. The next symbol is B, it goes to the next state. The next symbol is C, it goes to the next state. The next symbol is C, once again it is in state 4. The next C, it is in state 4. Next C, it is in state 4. Next C, it is in state 4. Actually, for the next A, it comes to 2, but it is not in the final state. So then it is not accepted. It is not accepted by the grammar. The next input is, it is a valid input. It is accepted by the grammar. Right. So the symbols used in the automata are the state. It is represented with the circle. A start state is left arrow without any label and circle. It is a start state. The accepting state or final state is represented with a double circle, and in transition from one state to another state, a arrow with the label of which token is moving. Right. So here in this example, it is for this finite automation is for identifier. So as far as any programming language, as far as Pascal is concerned, the first letter of an identifier should be an alphabet. It can be A to Z. So it starts, it is an alphabet, then it goes to the next state, that is state 2. The next input symbol may be an alphabet or digit. Any alphabet or digit, it again in the final state. Then suppose the input is sum, that is the token where name is sum, it is accepted by the grammar. So similarly, this is for an identifier name with underscore, right? So likewise, the next symbol is the for recognizing the integer value. So the digit 0 to 9, if the first digit is 0 or 1 or 2 or 3, it goes to the next state and it once again gets all the digits. So if it consists of only digits, it accepts the integer value, right? So similarly, the next one, the first digit should be either 1 or 1 to 9. If it is 0, it is treated as empty space. So from this above figures, you know that how a finite automata is represented. So figure A identifies all the identifiers and keywords. Figure B recognizes identifiers with underscore. In keyword, we know we have no option for underscore, but identifier we can have underscore. If the identifier has the underscore, the second automata will accept. The third automata, figure C, recognizes integers. It allows leading zeros, and figure D recognizes integers. It doesn't allow leading zero. So the finite automata provide an easy way to visualize the operation of a scanner. right? How the scanner recognizes the tokens, it traverses through each and individual character in the input stream, and when it reaches to a boundary, a blank space or invalid character, it stops scanning the process and convert it into a valid token. Then the next phase of the compiler is syntax analysis. That is the second step. So it analyzes the syntactic structure of the given input. Here the grammar plays the major role. It checks the correct syntax. Syntax means grammar of the programming language. So it checks with the grammar. So the output of the syntax analyzer is a parse tree or syntax tree. The parsing techniques are divided into two general classes, bottom up and top down. The top-down parser. Example for top-down parser is recursive design parsing. By the name itself, it uses the recursive procedure. Normally, the top-down parser starts from the root, right? That is the left-hand side of the expression, right? It finishes with the leaf nodes. It starts with the root. That is the grammar. In the grammar specification, we have the left-hand side, that is before double colon equal to symbol. It starts with the non-terminal given in the grammar, and it reaches the leaf node. All the nodes in the leaf are terminals. So it constructs the top down, the parse tree from top to bottom. And second one is the bottom up parser. The bottom up parser, example for bottom up parser is operator precedence parsing. We know that operator means that is plus, minus, star, slash, etc. So those operators has some precedence, that is the priority. So based upon the priority, it performs the in the language the operations has to be performed. The highest priority operator has to be executed first, then the lower priority. So normally in bottom up parsing, the parse tree is constructed from the leaf. That is the terminal nodes of the tree. That is the leaf nodes, and it convert it into non-terminals, and the trees grow from bottom to top. That is the leaf node to root node. Right. So now let us discuss the operator precedence parsing. It is a bottom-up parsing technique. This method is examining a pair of consecutive operators. Suppose in an expression A equal to B plus C. So it performs B plus C and assign the value to A. Okay. Suppose the expression has A equal to B plus C into D. Then it performs the multiplication operation first and then the plus operation. So the operator precedence parser has to determine the precedence relation between the operators. That is precedence relation based upon the grammar. As per the grammar, plus operator has lower priority comparing to star and slash. Right? So when an expression has both plus, star and slash, it gives the highest priority to star and slash. So to parse tree, construct the parse tree from the leaf node to root node. Leaf nodes has all terminals. The non-leaf nodes are non-terminals. So here it needs to construct the operator precedence table. Here for our above grammar, this is the relation grammar. So the equal to symbol means the relation is equal. Both the terminals have the same relation, equal relation. Here begin with for, begin has lower relation comparing to for. Suppose for with begin, there is no relation. So in some cases there is no relation, that is there is no way of occurring this type of cases. Suppose if it is appears, it is a grammatical mistake. So therefore constructing this table we need to follow some procedure. Here we are not going to discuss about that procedure. So equal to means those two tokens are equal precedence, having equal precedence. Then if there is no precedence relation between the pair of tokens, then those two tokens cannot appear together. Normally, the operator precedence parser uses stack to save tokens when it have been scanned but not yet parsed. The precedence relation hold only between terminal symbols. Only between terminal symbols. Right. The next one is shift reduce parsing. The shift reduce parser makes use of the stack to store tokens. Here in shift reduce we are using the input stream and a stack. Every symbol in the input stream is moved to the stack, and when it matches with the corresponding grammatical rule, it is reduced to the grammatical, that is the non-terminal. So right. So the two main operations or actions performed in shift reduce parser are shift and reduce. And shift means push the current token onto the stack. Reduce means recognize the symbols on the top of the stack according to the grammatical rule of that particular programming language and reduce it to a non-terminal. The next one is recursive descent parsing. It is an example for top-down parsing technique. Here, for each non-terminal, actually in recursive descent parser, it is a set of procedure. It is a set of procedure. Each procedure is meant for each non-terminal. Every non-terminal occurring in the grammar has an equivalent procedure. Here we are not going to discuss about those procedures, but each non-terminal is represented with a procedure. It constructs a parse tree from the root to the leaf. So root, it is a non-terminal. All the leaf nodes are terminals. Non-leaf nodes are non-terminals. Suppose for example sum equal to 0. So it is an assignment statement. So it starts from the non-terminal, that is assign. It is the assignment statement as per the grammar. The assignment statement is id equal to expression. Right? That expression is further expanded as term. The term is converted into factor. The factor is int. Here the value is 0. Sorry, it is wrongly given as 100. It is 0. Okay. The next step in compiler design process is code generation. The code generation is the last step of compilation. The code generation is performed by the code generator. It is part of the compiler. The code generator input is the parse tree and output is the machine language code. Each rule has in the grammar has a routine. When a parser recognizes some rule, then the corresponding routine is executed. Those routines are called as semantic routines. Whenever a system recognizes a grammar, it executes the corresponding semantic routines. Actually, the code generation technique is not dependent on a particular parsing technique, whether we can use either top-down parsing or bottom-up parsing, whatever it may be. The code generation technique doesn't bother about the parsing technique. The code generation routine uses two data structures. One is a list and another is a stack. So list, it is a first in first out, it performs the operations in first out manner, and stack, it performs the operation in last in first out manner. The next topic is machine dependent compiler features. The real machine dependencies of a compiler are related to the generation and optimization of object code. Actually, it is the machine dependent. Here, the code generated will be generated for the machine for which it is performing the compilation operation. Here, the machine dependent operations occur only in the code optimization. So optimization means how we can minimize the execution time, right? So here, the one of the machine dependent compiler feature is intermediate form of the program. Normally, the program is represented in so many intermediate representations. Here we are going to discuss about one of the intermediate representation, that is the quadruples. So the quadruples means each instruction is represented with four categories. That is, the first one is operation, the second one is operand 1, operand 2, and finally is the result. Here the operation is the operation to be performed. It may be plus, minus, star, right? The operation to be performed, and operand 1, OP1 and OP2 are the operands, and the result is the final value of the expression A into B, where here can be given as operation is star, A is operand 1, B is operand 2. Finally, the result is stored in result. The resulting value to be placed. Here the value, simple example, sum equal to sum plus value. Here the first sum plus value is evaluated. So sum, value, operands, then plus is the operator, and the result is stored in the intermediate. Actually this is a temporary variable. So intermediate variables, temporary variable I1. The next, that I1 value is to be assigned to sum. So the assignment operator I1 in Pascal, colon equal to is the assignment operator I1, no other operand, and it is stored to sum. So this is a simple example with quadruples. So here we can intermediate form of a program. It is depends upon the machine, because here the temporary results are stored in registers. So those register assignment will depends upon the machine architecture. Right. The second machine dependent thing is machine dependent code optimization. Optimization means minimizing the execution time of the program. So here the first problem is the assignment and use of the registers, and in which register has to be used, how we can minimize the execution time. Right. So here machine instructions use registers as operand or execute faster than corresponding instructions which refer memory locations, that we have already discussed in the first unit itself. In making and using register assignment, the compiler must also consider the control flow of the program, how the program flows, right? So here the program is divided into set of basic blocks. So the basic blocks are, it's a sequence of quadruples with one entry point, that is at the beginning of the block, and one exit point which is at the end of the block, right? So the code optimization means rearranging the quadruples before the machine code is generated. So the order of quadruples can be rearranged. Thank you. You go through this video and material. If you have any clarification, please make a note and send it to me. Thank you. Thank you for listening.